Apollonian Gasket. Let's start by drawing a circle, named C1. Note that we're not including the inside region as a part of the circle. That region is called a disk in math terms. Anyway, draw a second circle, C2, that touches C1 at just one point. We see that these circles are tangent to each other. You can even draw it so that either circle is inside of the other if you want. Now, draw a third circle, C3, tangent to both of the first two. Just make sure that it's not tangent at the same point where C1 and C2 are tangent to each other. Now that we have these three circles, we can always draw exactly two more circles that are tangent to all of the first three circles. This was discovered by the ancient Greek mathematician Apollonius of Perga, who lived from 240 BC to 190 BC. Because of this, when 5 circles are arranged in this way, they are called Apollonian circles, in his honor. Now that we have these 5 circles, let's keep drawing even more. Inside of the largest circle, but outside of all the circles contained within, there are 6 gaps that look like curved triangles. If we want, we can draw another circle inside each of these gaps, making the new circle tangent to each of the neighboring circles. Once we are done, we have created 18 new triangular gaps, which we can fill with tangent circles as well. We can just keep repeating this process on and on forever. And in the limit, we get an infinitely detailed shape, a fractal. This particular fractal is called the Apollonian Gasket. Golden spiral. Suppose you have two amounts, and the ratio of the larger amount to the smaller amount equals the ratio of the sum of the amounts to the larger amount. In that case, this ratio will always be the same special number, the golden ratio, denoted by the Greek letter phi. If we call the larger amount A and the smaller amount B, the golden ratio can be expressed by this equality. It equals 1 plus square root of 5 over 2, about 1.618. You may know about Cartesian coordinates, x and y. X tells you how far horizontally to go, and y tells you how far vertically. Another way to label points in 2D space is polar coordinates. Here's how it works. Starting from the origin, which is now called the pole, draw an infinite ray toward the right, called the polar axis. This system has two coordinates, r and theta. Theta is an angle, and r is a distance. To reach a point, stand at the pole and face along the polar axis. Rotate an angle of theta counterclockwise. Then walk a distance of r forward, and you're done. For instance, if the coordinates are r theta equals 390 degrees, then rotate 90 degrees counterclockwise and walk 3 units forward. Actually, mathematicians like using radians, not degrees. The number of radians in a full turn is 2 pi, also known as tau, which is about 6.28. Now, 90 degrees is 1/4 turn, which is tau over 4 radians, so the coordinates 390 degrees can be rewritten as 3 tau over 4. In Cartesian coordinates, an equation can be used to describe a set of points, like y equals 1 or y equals x. Similar equations are possible in polar coordinates, like r equals 1 or r equals theta. Let's examine another example, r equals 2 to the power of theta, generating a spiral shape. By definition, this can be rewritten as theta equals log base 2 of r. This is an example of a logarithmic spiral. The logarithm can be any base, and you can multiply r by a constant. One example is theta equals natural log of 3r, also written r equals 1/3 e to the power of theta. Here e is Euler's number, about 2.718. Now, imagine a logarithmic spiral that grows by a factor of phi each quarter turn. We want phi as the base of exponentiation, and each quarter turn should increase the exponent by 1. That gives us this equation, where we divide theta by 1/4 turn. And with that, we have the golden spiral. If you want to solve some geometry problems yourself, then Brilliant is a great place to start. Brilliant is a learning platform that focuses on interactive learning. Experience thousands of hands-on lessons in math, data analysis, programming, and AI. This approach has been shown to be 6 times as effective as lecture videos, and with each lesson building your way up from first principles, you'll gain a thorough understanding of every subject you study. Brilliant lessons emphasize critical thinking, so you'll learn by problem solving, not by memorization. With lessons that you can go through at your own pace, you can expand your knowledge in only minutes a day. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/thoughtthrill, or click on the link in the description. You'll also get 20% off an annual premium subscription. 3 torus. A torus is simple. It's just a donut shape. Note that the torus is hollow. If the inside is included, it's called a solid torus instead. Now let's imagine that the torus is actually a space. We will consider a creature living on the torus. Just as we can never leave our own space, this creature cannot ever leave the torus. However, it is free to move along the torus, and it has 2 degrees of freedom to do so. This is similar to a plane, which also allows 2 degrees of freedom for movement. Therefore, the torus is topologically 2-dimensional. One way to construct a torus is to start with a rectangle. Glue one pair of opposite edges together to form a tube, and then glue the ends of the tube together. Of course, the rectangle should be made of an elastic material for this to work properly. You could simply imagine the creature moving around on this rectangle, looping around when it reaches an edge. If it keeps traveling upward, it'll just loop back to where it began. The same for traveling rightward. The creature's universe is finite, but it has no bound. We can do a similar thing for a 3D object, a solid cube. However, this requires stretching and folding the cube up into a higher dimension, so it's harder to visualize. Nevertheless, we can glue each pair of opposite faces of the cube together, similarly to what we did for the rectangle. If we do this for the cube, the shape we get is called a 3 torus. Since you are a 3D creature, you can imagine yourself living in this space. Similarly to how the 2D creature could not see the seams while living in the 2 torus, you cannot see the walls of the cube while living in the 3 torus. In fact, they do not really exist to you. Within the 3 torus, you can simply travel forward in a straight line and loop back on yourself. In terms of our own universe, much remains unknown about its shape. Multiple different hypotheses have been proposed. One possibility is that it simply loops back on itself forever and ever, just like the 3 torus. Mucube. Think of the usual polygons: triangles, quadrilaterals, pentagons, etc. Using these polygons in 3D space, you can join their edges to form a 3D shape, known as a polyhedron. Each polygon is called a face of the polyhedron. If all of the polyhedron's vertices, edges, and faces are the same, it is called a regular polyhedron. More precisely, you must be able to move each vertex, edge, or face to another of the same while keeping the polyhedron identical. Imagine cutting off a corner of a polyhedron and looking at the cross-section. The shape you see is known as a vertex figure. For instance, if you cut off the corner of a cube, the shape you get is a triangle. The number of angles of the vertex figure is always equal to the number of edges of the polyhedron that join at the vertex. Now, the vertices of a polygon usually lie in the same flat space, or plane. In other words, they are coplanar. However, it is possible to have a polygon with non-coplanar vertices, known as a skew polygon. A polyhedron may be made out of skew polygons, or it may have a skew polygon as a vertex figure. In that case, it is called a skew polyhedron. In particular, it is called a regular skew polyhedron if the skew polygons in question are regular. An infinite regular skew polyhedron is called a regular skew apirahedron. Now, imagine an infinite grid of cubes, known as a cubic honeycomb. If you remove 2 opposite faces from each cube in a certain way, you will get a special shape called a Mucube, short for multiple cube. Any vertex, edge, or face of the Mucube can be moved to any other while keeping it the same, so it is a regular polyhedron, specifically a regular skew apirahedron. Burning ship fractal. You may recall the definition of the Mandelbrot set from part 1. Just to quickly recap, we chose a complex number c, and we defined a complex function fc with the equation fc of z equals z squared plus c. Starting with z equals 0, we applied this function over and over again. If we got a sequence that didn't diverge to infinity, then we included the number c as a member of the Mandelbrot set. The burning ship fractal is defined in a very similar way. The function is almost the same, but before we take the square, we first set the real and imaginary parts to their absolute values instead. That results in this function. Let's go through an example. Suppose we have the complex number z equals -3 minus 2i. The real part is -3, and the imaginary part is -2. Replacing each of these with their absolute value, we get the number 3 plus 2i. This can be represented graphically in the complex plane. We flip -3 minus 2i across the vertical axis, and then across the horizontal axis, so that it ends up in the upper right quadrant. Meanwhile, if we had started with a number like 4 plus 5i, that would remain the same, because taking the absolute values of each part doesn't change their value. Now we just have to evaluate the function as a whole on -3 minus 2i. The result looks like this. The rest of the process is just like the Mandelbrot set. We start by selecting a value of c, then we take this function and apply it over and over, starting with z equals 0. If the value stays bounded, then c is in the burning ship. Drawing all such values, coloring other values based on their speed of divergence, and vertically flipping the image because it looks nicer, we get this result.